Okay, so looking at the output stage of the class AB um, amplifier. So in this case, it's going to run class B. I'll go into that a bit more. But ultimately, we have 12 volts power supply, voltage divider here, so approximately 6 volts here. 2N3904 here, 2N3906, and I've just made these really low resistance for now. We will change that later. An output capacitor and an 8 ohm load. So the 8 ohm is trying to simulate being a loudspeaker. So, and on the input we have 4 volts at 1 kilohertz. So I'm going to simulate this, and if we look at the input, and then we look at the output, or before we look at the output, I guess it's important to understand that there's going to be actually just let's plug this in. So we can see here. Let me zoom in on this guy. So this is our input, and there's a dead spot here. So basically, as our input starts to rise, it's only when it gets above about 0.7 of a volt. Once it overcomes this, then this transistor turns on, and basically it's an emitter follower. It follows the input, but then when it goes below 0.7, it turns off. And the same at the bottom here. So this is basically class B operation. It's quite efficient, but it has this crossover distortion, which sounds horrible. So the idea is we need to set up something to overcome this, and that's what we'll do. That's what we'll do next. So what I'm going to do here, instead of this, I'm going to get rid of this resistor. Get rid of all of these, and then we put in a diode, then a second diode, and do another resistor, and then we'll add a ground. So what we're ultimately trying to do here is to barely turn these transistors on, so that we can ideally avoid that crossover distortion. So we're setting up this bias here, and we can disconnect that, and then we connect it to here. So can we pick a new diode? IN914 or 1N914, that'll do nicely. Not critical as to exactly what diode you're going to use. So now the idea is that the signal will come in, or sorry, we look at the setup here. So we have current flowing down here, and then we should have 1.4 approximately volts drop across this here, and current flows down to ground here. So if we look at the midpoint here, this should still be at 6 volts. The output should be at 6 volts. So this will be 6 volts plus 0.7. So this will just barely turn on this transistor. This guy will be 6 volts minus 0.7, and this is 6 volts, so that's going to barely turn on this transistor. So because 2 transistors are turned on, when we apply positive to it, then this guy should just continue to conduct, but conduct more. And when we apply negative, this should continue to conduct, but conduct more in the opposite side. So let's save this and run a simulation on it. So we'll just look at this point here first. And that's varying because of the, let's set this to 0 so we can look at our DC analysis first. So that's close enough to 6 volts. Let's look at here, pretty much the same. So now if I apply, and if you look at the voltage here and the voltage here, so we have this is on the negative side, so that's bias 0.7 below, this is bias 0.7 above. So now if I put this guy back to 3 volts and we run our simulation, I can turn some of these guys off. We just look at the input and the output now. So that's our input, that's our output. And what you notice now is the crossover distortion is now gone. And that obviously makes it sound a hell of a lot better. There's other ways of doing this. There's what's called VBE multiplier, and it basically uses a transistor and 2 resistors instead of here. It's probably a better option because you can adjust it depending here on these diodes having the same drop as these, and that's not necessarily the case, but it's close enough, and in reality it works just fine. Okay, so we're putting in a pretty high voltage here. So I want to change that. So I'm going to move this over here, and let's get rid of this. We get rid of this. Get rid of everything here. So then I want to put in another. I want to put a transistor down here. So let's do that. Where's this? So NPN, and I'm just going to do this by experimentation. I'm not going to do any of the maths for now. Pick values that seem reasonable, and we can adjust them as we go. So I want to bias this, so we need another two resistors here. And I just move this a little bit as well. So I probably should put a resistor in there. Let's try it without it first, and then we can add it in and see what happens. So let's just pick 100 ohms and 100k. And we just see what this looks like, and then we can take our input and feed this here. So now then the idea behind this is this guy will amplify what's coming in here and change this is basically the load for this common emitter amplifier. So I'm going to leave the setup the same here at 3 volts. I'm pretty sure we may start maxing stuff out, but I can adjust it down anyway. So save that. Run the simulation. There's our input. and our output. Okay, and as expected, we're we're maxing out because we've added in a lot of gain here. So let's change this down to 0.3 and simulate that again. And that's not enough to turn it on. Sorry, that's crazy stuff I did here. 100 ohms is madness. Let's put in 10k because we want about a volt here, give or take. So let's save that and run that again. Okay, we're still maxing out. So that's our input. So let's control the gain here. And let's put a resistor in here instead. And let's make this 100 ohms. Let's see. So the gain is basically this resistor over the equivalent resistance here. So let's try simulate this. So again, we'll take our input and our output. Okay, so we're still maxing out, but it's looking much more reasonable. So what is the voltage here? Again, let's do this at 0 amplitude so we can just look at the DC. There's probably people crying out there now because of the way I'm doing this, but it's more to get the principle of how this works. So, and as you can probably tell, I'm definitely not an expert on LT spice, but I know enough to be dangerous. So we want to look at our voltage here. So that's 10 volts. So that's too high, which means that. Sorry, let me just check. What is our voltage here? Yeah, so that should be about 6 volts. So we need to draw some more current. So let's adjust this guy to, let's say, 4.7k, and just rerun that simulation. That's gone. I'm gone the wrong way. So let's do 15k. Okay, so we're getting there. So let's make this 82k. Okay, so we're starting to get into the right zone. So let's make this 68k. Okay, so that's a bit low. Okay, so we go back to what did I have it at? I think it was 82. Okay, so and let's try 82 and 18 and see what that looks like. Yeah, so that's at 5.93, very close. We could keep playing with it, but so we're maintaining approximately half the voltage here and half the voltage here, which is what we want. So now we can adjust this guy again to 0.3 and simulate. So now we're getting a nice sine wave on the output, and so what is the voltage? The voltage is 1.5. So let's redo this again. So we look at our input and then our output. And obviously our output is a lot bigger and out of phase because of this guy. The common or the emitter followers will maintain the phase of the input, whereas the common emitter will invert the phase. But that looks pretty good. And okay, so that's we could leave it at that, but I would like to put a preamplifier here as well, so that we can, and put another preamplifier and then a pot, because we're still at like 0.3 or 300 millivolts, which is a lot. So actually, in reality, we need some proper resistance here, so I'm going to put this in at 4.7 ohms and 4.7 ohms. And let's run this again and just make sure it's still okay. And that looks good. So we have approximately 2.4 volts peak to peak, which is, and everything looks pretty stable. Okay, so we'll run with that, and then let me move this guy again. And okay, so we put in another transistor, NPN. I'm sure there's better ways of doing this, but it works, so I'm going to continue with it. I'm going to put two resistors here. I'm going to put one capacitor, and this is going to allow us to basically, vary the gain of this guy nicely, and another resistor here, and we want to bias this as well. Okay, so let's connect this guy up. So this can go straight to the base. And again, we'll bias this and we'll just play with it. Then we'll actually build it and see how it all works in the end. I'm going to put these straight up here for now, but in reality I would isolate these. I'd put a resistor and a capacitor here in just to stop, because this is drawing a lot of current, and you're going to find you can get motor boating and things if you don't isolate them. But I'll put that in shortly. But for in simulation, I don't think it will motor boat. I could be wrong. In fact, it won't, because it sees the wires as, I'm pretty sure, this is 0 ohm they're perfect in every way, so I think it won't. Okay, so let's start picking some values that we think are reasonable. So I'm picking 2.7. That's going to be pretty small compared to that, so we're not going to get huge losses. I do need to put a capacitor here to isolate the stages. So let's connect them. And let's just put 10 microfarad. So let's say we want a gain of approximately 10 here. So let's put in 10 microfarad, and so let's make this 270. So our gain is going to be this over this guy approximately, and let's make this guy, don't really know, let's do 1K. So I'm just going to pretty much randomly pick stuff here. 12K and 100K. And again, we'll adjust all this, change the pick a new resistor to N3904, and we can look at the DC biasing. So let's save this, set this down to 0. There is a DC bias option in simulation as well, but I actually find it easier to, I find it handier to do it this way. So let's look at what voltage we've got here. Okay, that's too high. What have we got here? That is 1.2 volts, and on the emitter, don't want the current, I just want the voltage. So on the emitter we got 0.63. So we're too high here, so we need to draw more current. So let's start adjusting this down. So let's try 68K. Okay, so we're now down at 9.6. It's still not enough. So let's do 47K. Okay, we're getting closer. I think more of my problem is here, to be honest. So let's do 470. Okay, so we're getting slightly more reasonable numbers. So the collector voltage is just under 6 volts, which is here, and I can just change this to a 10K maybe. It'll make it all perfect. There's not a lot of point in trying to get everything perfect. Nope. So let's go. So 47. So 56. Okay. I'll probably find where I was. $12K, and let's run that. And what was, I had this at what, 68 I believe. Nope, no I can't remember. So that's 68K, and it's, so getting confused now. Okay, so we're at almost 8 volts, and I wanted to go down. Let me just make sure yeah, I'm gone the wrong way. So I think I'm at 47 for now. So let's run that. Yeah, okay. It's close enough. So now let's look at where we are here. Okay, so this is our preamplifier. So let's turn on 0.01, 10 millivolts on the input, and save that and simulated. So that's 10 millivolts on the input. Let's see what we're looking at here. It's a lot more. Not exactly sure what it is. We can dig deeper, and finally we look at the output. So the output looks pretty good. So it's, what voltage is that? Possibly a quarter of a volt, half a volt peak to peak. So I think we need more gain. So we basically have a gain of 10 here. So if I change this to let's say 47 ohms. Simulated. Okay, so now we got approximately. Okay, it's not symmetrical, and I'm not sure why. Actually, I think we mean there's the thing that happens in these, which if you don't bootstrap them, they can. Or actually, let's see. Sorry, that's just the startup. So we're at 1.29 there, and minus 1.2 to, yeah, okay, it's symmetric. It is symmetrical. Sorry, that's the startup voltage. Okay, so that all looks pretty good. There is something that is important as well, which is as we start to increase the voltage here, if this voltage here, because this transistor turns on, the voltage here is going to, let's assume it was fully on, well, the voltage here would be 12 volts. But you can no longer turn this guy on, because best case you got 12 volts here. If 12 volts here, this transistor is off. So in reality, you need a higher voltage here to turn this transistor on. So you can't get rail to rail. Now we definitely don't want rail to rail with 2N3904, 2N3906, and an 8 ohm resistor, or we'll have rail to rail smoke. But it's just to understand it more than anything. So if we start to, let's say, make this, and I'm pretty sure this. I just want to find the point that it will, just before it starts clipping. Okay, so it's well clipping there. So 0.05. Let's see. Let's run this. Still there. 0.02. So 20 millivolts on the input, and you see it appears to be starting to clip at the top before the bottom. And you can, let's see. So we're at, what are we at here? We're at I'm looking down in this area. So we're at minus 2.288, and at the top we are 2.26. So I think it's starting to clip there, but let's see. So 0.25. And it's clipped in both of them now. Might be worth, just for simulation purposes, just making this really small, because these do have an effect on it. So let's run that again. Yeah, so you can see it's clipping at the top before clipping at the bottom, and that's a problem. Now, for this type of very low power amplifier, it probably doesn't matter, because you're not going to have huge swings of voltage here anyway. So we need to add in some protection resistance here, because if we get 12 volts here and both of these turn on at the same time, or we get a full load in here, we're going to exceed the maximum ratings of these. And in reality, the proper way to do it is actually have a current source here, to, you know, if you want to, if the maximum current we want to flow through these is, let's say, 200 milliamps. So you put a 200 milliamp current source here, and that is the best way to do it. But I want to. So what I'd like to do is what's called bootstrapping. So let's get rid of this resistor. Try to fit two resistors in here now. So it was a wire I was looking for. So that was overall 1K. So let's make this guy 470R. 470R, and nothing should change. Okay, it's slightly 60 ohms different, but I don't think we're going to see a whole lot of change. And I can't remember what the blue guy was there. So anyway, let's just look at the output. So nothing has changed. So now, what I'm going to try to do is, I haven't done this before. I've read about it, so you have to forgive me if it doesn't work. So we put a capacitor here from the output. And I believe it's connected to there, not to here. But I might be wrong on that. Okay, I'm just gonna try it. So I'm gonna pick 10 microfarad again. I really don't know. So the idea behind this bootstrapping is that you add voltage here into this. So the voltage at this point is going to go above the 12 volts. It's probably easier just to simulate it and show as opposed if it actually works. So the last time it was clipping on the positive. Now it's clipping on the positive and the negative, but we've got a lot more voltage on both. What voltage is here? Yeah, so we're getting an extra two volts here. You can see, but it's clipping on both, and really what I want to do is have it clipping equally. So let's see if we can change this to 0.2, and let's, okay, so it's now going plus or minus 4 volts, and it's clipping. You can see there is some distortion starting to kick in, so 0.22. Let's simulate this, look at the output again. So now you can see it's starting to clip at the top and the bottom at the same time. And that makes sense. So just have a look at the voltage here. Yeah, so we're going up to, we're down to 6 volts, but we actually get 14 volts. And you can see we get it when we need it from the, this is when we're going high. And it just allows full output swing. Now, as I say, for this particular design I'm doing, I don't think it's necessary because I'm going to put some protection resistors here. So let's put these back in. So 4.7. So it'll be interesting to see. I haven't done this before, so just really concerned with the output here. It should be lower now. So it's clipping at both, and that's because we've added the resistors. But the clipping seems reasonably even. Maybe not exactly. And so we've plus or minus 2.5 volts. So let's try 20 millivolts in. Yeah, okay. That looks pretty good to me. So this is our input. So we're at 10 down to just 1.5 or yeah, okay. I think I'm pretty happy with that. So that bootstrap, I say I haven't done it before, but it's a really nice concept. And if you're doing higher power, let's say you're going to use a BD139 or is it or tip for is it 40 or 41? I can't remember the name of them. They're higher power transistors, and you want to get you do want a decent voltage swing here. Then you are going to need to do something like this. There are other methods there, but it's what do you call it? For this, I don't really think it's necessary. Okay, so I'm just going to do one other thing here, which is replace this with a what's it called? VBE multiplier. Okay, so for the VBE multiplier, basically what we're going to do is replace these two diodes with a transistor. So I just move these guys out of the way. We'll add in a NPN. And we want it around there, give or take. And then we want a resistor, another resistor. And we won't see any real change in the output here. Ooh. Because I'm guessing that in simulation the diodes are all pretty perfect and match. Okay, so what have we got here? We have added an extra transistor. So if we change this, let's say to 1K. So we have 0.7 of a volt from here to here across the base emitter. So the current is the voltage divided by the resistance. And that's going to come down from here. So if we put in the same value here, let's say 1K. So we've 0.7 volt drop across this resistor because of the diode. Well, because the current's flowing down here, we have to have 0.7 volt drop here. So now we've got 1.4 volts here, the exact same as with the two diodes. The difference is if we make one of these a variable resistor, we can adjust the voltage here. So it could be like 1.2 or 1.8, and that's important because you barely want to turn these on, just enough to have them operating in the linear region. If you turn them on too hard, you're basically you're going to be wasting a lot of current if there's no input signal. There's still a lot of current going down here. So let's look at this, and we can play with it for a minute. So sticking with the 2N3904, and I'm guessing that we're going to see nothing different. If we do, I'd be surprised. So the output, and again, let me just run this again. So let's look at our output, and there it is. So now if we look at the let's start looking at the DC voltages here again. So we do this, and what we're interested in is, so we know we've 12 volts here. So what have we got here? So 6.93, and then at this side we have 5.5. So if we add in 1.4 is the difference between the two of these. So let's say, for the sake of our argument, we wanted a much higher. We wanted three voltage drops, and so sometimes if you've Darlington on the output, you might want 4 voltage drops. So let's say I'm going to make this a 2K. So right now we're approximately 5.5 to 6.9, which is 1.4 voltage drop. But now if I run this, we're going from approximately 4.9 to 7.1 maybe, which is 0.21 give or take. Yeah, so it's three volt. This is now the equivalent of 3 diodes. So if we were to make this, let's say for the sake of argument, a 2K variable resistor, we can change the bias current or the bias voltage here just by adjusting that pot. As I said, in reality, I have found the diodes work fine, but I think if you're doing for mass production, temperature changes, you name it, then it's a different story. Okay. So, is there anything else to cover here? If this was a single-ended supply or a dual supply, you'd basically change these to the negative, and then you wouldn't need a capacitor here because this would actually be at 0 volts. But I'm going to stick with the single-ended supply. So let's put in 5 millivolts, and let's just have a look at what the signals look like. And that looks pretty good to me. So we're looking at, again, sorry, let me just click the output here. Yeah, that looks nice. As we drive it harder and harder, we're gonna add in some more distortion. So let's put in 10 millivolts, and that's still looks pretty good to me. I'm not doing any of the calculations on this now. Oh yeah, sorry. There's one other thing. Again, it won't make any difference to what we see in simulation, but it will make a difference in real life. So I'm going to cut this guy, place a resistor, place a capacitor, and a ground. And let's wire this up. And so I'm going to make this 470 ohms. Make this 100 microfarad. Actually, there's another thing to it. I've seen it done where you put like a 4.7K and a 0.1 to ground here. It might help a little bit with noise in the system. So I said this is basically the voltage shouldn't come in this way then. So let's disconnect that guy. We don't want a 470 ohm drop on the high power, but it's fine here when the currents are really low. So let's move this guy to the opposite side. Okay, so we have 12 volts here, and then we're going to get a lot of current fluctuation here, and if this isn't perfectly zero ohm, which it won't be, that's going to occur here, and that's going to be coming into the the base and so on, and that's going to get amplified. It's going to pass through here, get amplified more, and you basically end up with feedback within the system, and you can end up with an oscillator where it'll motor both at the audio frequencies. So this shouldn't make any difference really to the output. Really interesting to see what this is here. So yeah, so we have dropped a little bit, but the capacitor is keeping the voltage stable because there's not a lot of current here. Don't actually know how much current is here. Okay, so was it plus or minus 2.8 milliamps approximately, and what current have we got here? So on this guy up to 180 milliamps. Now from what I remember, the 2N3904 I think is rated for 200 milliamps, and same with the 2N3906. So we'd be right on the limit at that. So that's about as much as you can get out of it. Let's look at on the capacitor. So we have 160 plus or minus 160 milliamps, and yeah, okay. So let's just do a final view of the circuit, and I like the idea of this guy here. It just means you have that's NPN. Let me just, I don't think it's going to make any difference, but just to be sure, I forgot to change him. So let's simulate that and just have a look at the output. So what just happened? It's a different characteristic completely. Okay, just when I thought it was done. So let's have a look at the DC stuff here and see what's happening. So but at this, let's re-simulate. So where are we really interested in looking at the output voltage? And that's 2.4, which is a bit low. The voltage there is the same. Okay, so our current for this guy, I'm not sure what the generic NPN is, so let's change this to 10k and resimulate. Okay, so that's not so 12k, and we're pretty close. 11k. So we're just above the 6 mark, and let's see, does that 0.01, so 10 millivolts. Simulate, look at the output. Okay, all back back to normal. Uh, yeah, I'm not sure of the characteristics of the standard NPN, or is there? Let me just add one here just to see. 'Cause that's NPN. It doesn't say. So I don't know. But either which way, I will build this and test it out and see how it operates. And yeah, I think it's a fantastic tool to learn how to design transistor circuits. And I say I haven't done the maths for this. I will at some stage, but in my experience is that it's a great first place to start with this, and generally you don't have to change that much. So you don't. I mean, the key for this is you need enough current flowing through this to feed the two amplifiers here, or the two output transistors. So this needs to be reasonably low impedance. If we put these up to possibly 10k or something, you wouldn't have enough current flowing. Let's say these have a beta of 100. Well, you need to be able to put in a milliamp in here if you want 100 milliamps to it. And 10k won't give you that. If actually it'll be very close. Anyway, so then just setting all the bias points. Let's just have a look. Just make sure that everything looks reasonable at DC. So simulated. So we're looking at this. So that's 3.36. I would have liked that to have been about halfway. Not the biggest deal in the world. This is important. So it's about the 6 volts. Similar there. Yeah. So this one. So we're drawing too much current through it now. I thought I checked that earlier. Maybe I didn't. So let's look at this again. So we have, let's measure here. So that's 1.39. Yeah, that seems a little bit too high. I think I might have had this right and I started messing with it, and 10k, so simulate again. So we're at 4.8, so let's do 8.2k. Okay, so we're at around the 6 volts, which is, it's central. It doesn't really matter because in this case, you put in a very small voltage. You're never going to get a big swing here anyway. So you're not, because if you did, the whole thing is overloaded. Okay, I'm going to cut it at that, folks. But nice way of designing a Class AB audio amp without any calculations whatsoever. And the only other thing is we should put a pot here in reality, so that we feed it in and we can adjust the volume. Then strong signals will obviously overload this, so we can adjust it with the pot. Okay, that being said, thanks for watching. Really would love a few comments. I'm pretty new to I've never done audio amplifiers before, so or never done discrete. Always used the ICs, but I just fancy the challenge of doing a discrete one. So I'll build this and I'll put that up on a different video. Okay. Thanks for that. Catch you all later.